Welcome to lecture 23. In this lecture, we will continue the discussion on graph traversal methods. So we will talk about an algorithm called depth search. The nickname here is DFS. So DFS is another simple method that finds all the vertices reachable from some source vertex. Let's call it S. So the basic idea here is that when we try to visit starting from S, we will go as deep as possible, exploring a branch as far as possible before we start exploring another branch. So we will see an example of what is meant by branch and then what is meant by as far as possible later. Okay, we can quickly look at the pseudocode for this DFS algorithm. So depth search algorithm can be written by using a recursive method. So in general, when we perform depth search at the vertex u, we can make sure that u will be the first time that we try to visit it and then explore starting from it. So for the first step, we will mark u as discovered. So basically, a node will have several status. Either it is discovered, or it is finished, or it is fresh. It is not discovered and not finished. So at the beginning, when we enter this recursion loop, we will have u marked as discovered. And after that, we will check each neighbor of u. So for a neighbor of v, we will find out whether v is finished or not and discovered or not. If it turns out that v is something that we have not seen before, v is not finished and also not discovered, then we will continue to perform the DFS starting at v. So we will move from u to v and try to work to explore starting at v after that. So once all the neighbors of u are checked, then we are done with u. So we will mark u as finished. So this is the simple recursion. And then if we want to explore the whole graph starting at vertex of S, then we will call DFSS at the main loop. Okay, so here is an example. So this graph tells us that, okay, this is an example graph and assume that S is the source vertex for this problem. So at the beginning, we will mark S as discovered. So once we have done so, then we will check the neighbors of S one by one. So in any order that will work. So here in the example, we will first check W, which is the neighbor of S. So we will have an arrow here that helps us to recognize that, oh, W is being checked. It is due to S, because when S is visited, then we are looking at the neighbors of S and then we find out that W should be checked. Now when we are at W, we will continue the same idea, the same process, and find out the neighbors of W. So W has S as a neighbor and X as a neighbor, but here only X is an undiscovered and also unfinished vertex. So in that case, W will try to visit X, so we will check X. So in that case, X is now discovered, and this arrow tells us that, oh, W is discovering X. And after that, we will see that if we are starting at X, we will find out the neighbors of X, but then we find out that X should now discover T. So this is what we see, X discover T, and similarly, T discover U, and then U discover Y. So this is what happens when we are doing here. Now at this moment, we will find out that Y doesn't have any further neighbor to discover. So there is nothing to be done. So in that case, all the neighbors of Y are now being checked, so we will mark Y as finished. So in the next step, Y is now finished. When Y finished, we go back. And then now U will not have any further neighbor to explore, so also U will now be finished. So U is now finished, and then T is finished, and then X is finished. So in the next graph, X is finished, W is finished. Now at this moment, we have an interesting point. So we go back to S. Now at this moment, S will not be finished at this point. It is because at this point, we find out that S will still have some neighbor that is not finished and not discovered. So in that case, S should discover R. So now S discover R, and then R continue the problem, the procedure. R will discover V. R discover V, and now V finished, R finished. Now at this moment, we are now back to S, and then we will see that S do not have any further neighbor to visit. So in that case, S will also finish. So in that case, this is how the procedure works. So we will see that, so when we are at location S at the beginning, so let's get back a little bit. So this is the first page. At this point, S has several neighbors that you can do, but then what we are going here is that we will try to visit the nodes, and without going back. If there is a way to go forward, we'll go forward. We go as far as possible until we don't have any further branch. Then in that case, we will explore another branch. So this is how this DFS idea works. Now again, just like BFS, we can maintain something called the DFS tree of S. So this is basically the directed arrows that we find along the DFS process. So we have S discovering W, W discovering X, and so on and so forth, and later S discover R, R discover V. So this will now form a rooted tree with S being the root. And this tells us that these are all the nodes that is reachable from S. Okay. Now the correctness of the DFS is based on the theorem below. If U can reach V by some path P of unvisited vertices, then so U is the starting vertex. If U can reach V by just using the unvisited vertices, then all the vertices on this path will be discovered by the DFS starting at U. So if you think of unvisited vertices as something that is uncolored, white, then if U can reach V by a sequence of nodes that are white, so we can call it a white path, then the whole path will now be discovered by U when we perform DFS on U. So this is called the white path theorem. Okay, now the proof of this white path theorem is actually very simple. We can prove it by contradiction. Okay, so let's imagine that we have a certain white path. So we let P to be a white path such that V0 is U and then Vk is the V, and then we say that P is a white path so that we will start at V0, V1, V2 up to Vk. So all the nodes in between, they are all white. They are all unvisited. So that means that they are not discovered and also not finished. Okay. Now, so V is some vertex that is, of course, this is going to be discovered because when we run DFS on U, so V0 will be the first node, which is U, and it is automatically discovered immediately. But then we try to show that, okay, there is some node on this path that is not discovered by the DFS on U. So in that sense, because the starting vertex here is discovered, so if this happens, so there must be some node undiscovered, and then we can actually find out the first node on this path that is not discovered. So we will let Vj plus 1 to be such a node which is not discovered, but the node that is before it, the Vj, it is discovered. So this must occur. Okay? Now, if this happens, then what does that mean? Because Vj is discovered, so when Vj is discovered, then we automatically will run DFS on Vj, right? Because it is discovered when it is run by DFS. So when it is true, then all the neighbors of Vj will be checked. So all the neighbors of it will be discovered. Then in that case, it is impossible that Vj plus 1, which is a neighbor of Vj, is not discovered. So in that case, there is a contradiction. Okay? So that means that, okay, that means that all along the path from U to V, If it is formed by only white nodes, then all the vertices will be visited by, this DFS starting at U. Okay, now the correctness, now with the white path being shown, the correctness of the DFS is now very easy. Because at the beginning, at the very beginning, all the vertices are unvisited. They are all white. And then what will happen next is we start performing DFS on S. So S will now be discovered. Then still, if any node that is reachable from S, then there must be a path from S to that node using only the white vertices at this moment. So by white path theorem, the vertex of V that is reachable from S will now be discovered by the DFS on S. Okay, so in that case, S can reach V if and only if V is discovered by DFS on S. Okay. Now let us take a look of how we can efficiently implement this DFS method. So first of all, remember that we will need to keep track on the status of a vertex, whether it is discovered, finished, or fresh. And this can be easily done by maintaining an order V size array. So we will just have a bit vector or whatever, so we can have an array that keeps track on the status of each vertex. And then when we run DFS, we apply recursion as before, although we can also use a stack. So we will leave this as an exercise for you. And then if we look at the time, okay, so the best way to analyze this recursive method is we find out that how much work are done with respect to the vertex and with respect to the edge. So first of all, for each vertex, it will be discovered at most once. So in that case, the time that we spend on the vertex, if you count it like this, the discovery time, line 1, it is done only order V times. On the other hand, each edge is being checked at most twice. So when we will be checking an edge, because when we are trying to perform DFS on the vertex V, we will look at all the neighbors of V. So in that case, we will check each edge that is connected to V. So in that case, an edge is checked at this point if it is linked to the current vertex being checked by DFS. And then we will see that each edge, there are two endpoints. So an edge is checked when either of its endpoints is being the DFS source. So in such a case, each edge is being checked twice. So altogether, the running time is proportional to the number of vertices and the number of edges, and then it is order of V plus E time. And actually, the DFS method can be used to find all the connected components of a graph G. And then, so just like the BFS, we can also do so. So here, if we apply the DFS method, it is also very simple. So we will check for each vertex of U. Okay, if U is not visited, so U is not discovered, not finished, so it is not visited, then we will run DFS with U as a source. So after this step, then all the nodes reachable by U, they are now visited. And after that, when we enter this for loop, we'll then look at the other vertices one by one. And as soon as we find out some vertices that we have not seen, we will start running DFS on that vertices and then mark some of the nodes as visited and so on and so forth. And by each time when we run this if loop, okay, so when we actually, by each time when we run DFS, then it means that we have now discovered a new connected component. Okay, so the total time for this method is still linear. It is because the time to run DFS is proportional to the number of edges of that component rather than the number of edges of the whole graph. So in total, the time that we spend, although we are running DFS many times, it depends on the number of connected components, the total time is still linear to the number of vertices and the number of edges. Okay, so that's all for this lecture. Thank you.